So, my name is David. I am a PhD student in Scuola Normale Superiore Pisa, and today I will talk to you about parameter estimation from 3D cosmic 21 centimeter images with neural networks. So, just for the introduction, we know that cosmological 21 centimeter signal is a physics-rich probe, and that it encodes both cosmology and astrophysics in its signal. And here I am showing just an example of some simulation of such signal. And what we know is that it shows non-Gaussian properties. And what we are trying to do is we are trying to see how to infer cosmological and astrophysical properties optimally. On the story of Gaussianity, we saw today a few examples. Here I'm showing it on an example of a duck. Let's say that we would like to infer some of its properties, for example, length of its neck or size of its eye. And so let's imagine that we take this image, we Fourier transform it, change some phases, and at the end return image space, and we could produce image that is shown on the right. And so both of those images have the same 2D power spectrum. However, we can clearly see that if we want to infer properties of a duck, we should use some non-Gaussian statistics beyond power spectrum. Considering 21 centimeter signal, we are lucky that it is much simpler than example of a duck. And so we know that also power spectrum encodes large amount of information, and there were a lot of researches going which provided good inference only with power spectrum. However, as we know that we lose some information, then there were also a lot of advances in using, for example, bispectrum or some morphological spectra for such tasks. And what is conclusion of this research is that non-Gaussian statistics do actually improve parameter inference of our astrophysics and cosmology. However, if we push this a bit further, we know that without good a priori physical motivation for some summary statistics, we cannot say what is the optimal one. And so we can choose some relatively ad hoc. And therefore, what is approaching our research is let the machines figure that for us. And by machines, I refer to neural networks. We are obviously not the first one who got with this approach, and here I'm listing some of recent results applied to 21 centimeter. What we specifically introduced in our field is usage of recurrent neural networks. So recurrent neural networks are specifically designed to deal with sequential data, and some applications in industry involve encoding both audio and video information, or also in language processing. And so here, to slightly explain you how it works, each recurrent neural network has something that's called its hidden state, or its type of encoder of information. And what it does is that we are passing some vector at some time step inside of it, and we combine it with its hidden state. And after computing some activation, hidden state is updated, and it gets the knowledge of this input vector that we got into. And for example, if we enroll this in several steps, then we can see how one vector passing through the network updates its hidden state, and so on until the end of the series. What we used in this research specifically is long short-term memory cell, which is dealing specifically with exploding and vanishing gradients problem and long-term dependencies. Applied directly for light cone object with which we are dealing. The way we are encoding information across frequency bins is using RNNs, because the frequency bins are type of sequential data. And what is good with RNN is that such correlations are encoded across all frequency bins at once. And moreover, what we do is that in sky-plane direction, we are using 2D convolutional neural networks to encode local correlations in the image. To move on our procedure that we used, so we are calculating 10,000 21 centimeter fast simulations, varying astrophysics. And we are computing three-dimensional light cones out of it. Then we are passing those light cones through observational pipeline by adding noise and foregrounds. And then we are trying to use our neural networks to encode information from such objects, and at the end, infer astrophysical parameters. Considering our observational pipeline, we are investigating 3 levels of contamination of our signal. So we are starting with cosmological signal, and first step is to remove global signal, because for example, SK telescope is not sensitive to the mean of one frequency bin. Then we are adding square kilometer wave noise, which also reduces some of its properties here in lower redshifts, but also adds noise in higher redshifts. And at the end, we are removing modes which are highly contaminated with foregrounds by removing all of them below horizon wedge. At the end, we construct several architectures, and we train all of them on all 3 levels of contamination. And in that way, we are trying to infer what's the effect of such contamination. Considering astrophysical parameters, we are varying both UV and X-ray properties of the galaxies, and also its star formation properties. And such parameterization is simple, but it does show important changes in timings and morphologies of our signal, and that's why we believe that our inference will be robust. To show you an example, here I'm showing how minimum virial temperature for star-forming galaxies is changing the signal. And what we can see is that if virial temperature is quite high, then galaxies will be lightened up quite later on, or if it's low, it will be lightened up earlier on. And such property then changes all epochs of our signal. And what's more important is that also morphologies are highly changed, and therefore we believe to be able to infer such parameter quite well. And this is actually the case. So here I'm showing you results for the database without global signal. So what is shown on x-axis is this minimum virial temperature for its predicted value, and what's shown on the y-axis is probability of true values given predicted values with the same units of kelvins. Different colors show 3 architectures that we constructed, and they are differing slightly in the way they are incorporating correlations along frequency beams. And with gray are shown similar recent results. What we got from this research is that we improved variance by a factor of 2 to 8, depending on the architecture and the actual parameter inferred. And that taken in account that here we don't have global signal, and we used boxes with 4 times less resolution. Furthermore, when we compare it to other levels of contamination, we can see that larger data contamination versus the inference, which is quite expected results. But what is very nice is that, for example, even in pessimistic foregrounds regime, we are able to infer those parameters in decent level. And moreover, we can see that networks are having problem in inferring some specific ranges of our astrophysical parameters. And that means that we are hitting the limits of our data set. At the end, to conclude, main result of this research was to introduce RNNs, which are optimally suited to encode information from the objects such as light cone. And by this, we improved by a factor of 2 to 8 our previous results, which are good even in the case of pessimistic foregrounds. And at the end, if we would like to improve those results, we should have better augmentation both of telescope noise and foregrounds, and in the number of cosmological simulations of the signal. Thank you. That's all.